My name is Alex Wade with the Chan Zuckerberg Initiative, and I'm extremely excited to announce our closing keynote speaker for the day, Katie Bouman. Katie is a Rosenberg Scholar and an assistant professor in the computing and mathematical sciences, the electrical engineering, and the astronomy departments at Caltech. Prior to that, she was also a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. And today she's going to describe to us the methods and the procedures that were used to produce the first image of a black hole from the Event Horizon Telescope. Spoiler alert here, they may have used just a tiny bit of open source software in that massive effort. And she'll also be telling us a little bit more about the future of black hole imaging. So welcome, Katie. Thank you for joining us today, and I will hand it over to you.
Yeah, thank you so much for the invitation to talk to you today and for the kind introduction. So I work in an area called computational imaging, where we design hardware and computational algorithms to recover images of things that are not possible to recover with using traditional sensors. And so I like to work on what I like to call imaging the invisible. And that's on ranging from problems on what can you extract using the camera in your back phone pocket, in your phone in the back pocket, to medical imaging or seismic imaging. But today I want to tell you a bit about how we used a computational telescope and a network of people from around the world to see what I think of as the ultimate invisible phenomenon, black holes. So black holes are one of the most mysterious phenomena in the universe, and scientists have been studying them ever since they were predicted from Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying this giant elliptical galaxy that's at the head of the Virgo constellation. This galaxy is called M87, and it's really special. It's 55 million light years away from us. And over 100 years ago, someone discovered this streak of light that was on the sky that ended up being this galactic scale jet of plasma that was shooting out of the core of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists developed better and better instruments to try to study the supermassive black hole and the jet that was coming out of it. And then in April of 2017, we hooked up this Earth-sized telescope and collected the data necessary to make the first picture of black hole. And then 2 years later, after processing the data, this is the image we saw. And this black hole image, as I'm sure you all know, is the result of the hard work of over 200 astronomers, physicists, mathematicians, engineers, from all around the globe that worked together to achieve something that wasn't possible for any one person to do. We had to bring together all these different kinds of expertises, and we brought together people from North and South America, Asia, Africa, all across Europe to make the picture a reality. But really, this picture isn't complete, and that's not just because there are some people that happen to not make it into the photo. It's because the picture wouldn't have been possible without the decades of hard work from our extended team, the online community of open source contributors whose work we built off of while developing new tools and techniques for collecting and analyzing the black hole data. And so today I want to tell you a very abridged story of how our team, this extended team, was able to work together to take the first picture of black hole, and also kind of a hint as to where are we going next. So the first question you might ask is, how are we able to take a picture of a black hole that by definition should be unseeable because light does not come out of it? And that's, well, light propagating near a black hole doesn't actually follow straight lines. They're curved because the black hole is curving space-time, and photons can even go in complete circles around it. So you have the space around a black hole. It's actually lit up by this hot gas that's spinning around it. It's heated to hundreds of billions of degrees. And so you have these photons flying around everywhere. Some of the photons fall into the black hole, but other ones just graze it and are bent by the gravitational pull, such that the net effect is essentially that the black hole casts a shadow on this backdrop of the hot material that's almost perfectly circular. And if Einstein was right about general relativity, then this light would be bent into a ring whose size and shape tell us about the mass and the spin of the black hole. And this ring is referred to as the black hole shadow. Now, this is not really what we'd expect to see exactly. Simulations of looking at turbulent plasma in the jets and in the accretion disk around a black hole, computational theorists predict that this is really kind of what is closer to what we would see if we could see it around a 1 millimeter wavelength, and we were, could see with that kind of resolution. But even if the black hole does make this imprint that we should be able to measure, taking a picture of this ring is still incredibly difficult. And that's because this ring is super, super small. It's about 40 microarcseconds in size, which is about the same size as a grain of sand. But if that grain of sand is in New York and I'm viewing it from where I am in California. So taking a picture of something that small is really hard. And the reason it is it all comes down to the limits of diffraction, which say that there are these fundamental limits to the smallest things that we can possibly see. And this governing equation says in order to see smaller and smaller, we have to make our telescope bigger and bigger. And so if we plug in the wavelength and required angular resolution that we need to see that black hole shadow into this diffraction limit equation, you can easily calculate that in order to see that ring, we need to build a telescope that's 13 million meters across, or essentially the size of the Earth. And if we could build an Earth-sized telescope, we could just start to make out that distinctive ring of light that's indicative of the black hole's event horizon. Okay, so although building a single dish telescope the size of the Earth is impossible, by joining telescopes from around the world, this international collaboration called the Event Horizon Telescope Collaboration built a computational telescope that's the size of the Earth and was capable of resolving this structure on the scale of a black hole's event horizon for the first time. So how does this computational telescope work? Well, all of the telescopes in the worldwide network kind of work together. So they are linked through the precise timing of atomic clocks that we put at each of the telescopes. And then teams of researchers at each site essentially freeze light by recording the data on petabytes of hard drives. And then we bring it all together and use our computers to act like the lens to make that final picture. And so my primary role on the project is on developing algorithms to fuse the data from telescopes to make a picture. And so how do we go about doing that? Well, unlike in a camera, the Event Horizon Telescope doesn't capture the picture in pixel space, but instead in its frequency space. So we are essentially taking measurements of the black hole image's Fourier transform. And if we tiled the globe with telescopes, if we put them everywhere on the globe, then we would sample all these spatial frequency measurements. But since we only have telescopes at a few locations, that means we only get a small number of measurements. And so it turns out that for every 2 telescopes we have in the telescope array, we obtain a single measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. So we'd like to get all these measurements. For every 2 telescopes, we probe one spot there on that measurement plane. And since each of these measurements is complex, they're described by 2 numbers, the amplitude and phase, which you'll just want to remember for later. Okay, so in 2017, we observed with 8 different telescopes, but actually only 5 of those telescopes were at different locations and could see the black hole in M87 in particular. And so that would only be 5, choose 2, only 10 points that we have to try to make an image from. But luckily, as the Earth rotates, we actually obtain other new measurements. So since the baselines between telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the spatial frequency plane, where telescopes that are close together tell you about broad structure in the image. And so to get the fine detail, you need to put your telescopes far apart. And so at this point, we have the data and we can kind of abstract away all the astrophysics of the problem and think of it as a purely mathematical problem, this inverse problem. We have sparse data and our challenge is to find the image that caused that. And if we were given measurements that covered the entire frequency plane, it would be trivial and we could just invert the data to give us back an image. But since we only see a few samples, that means that there are an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, there is a different and quickly changing atmosphere above each of the telescopes across the globe that causes our data to be really noisy and makes the problem even more ill-posed. And so what does this noise look like? Well, I like to explain a little bit about how the noise enters our system because it kind of informs how we go about doing the reconstruction problem, how we went about imaging. So the whole reason that the Event Horizon Telescope works in the first place is due to the fact that light from the black hole, it's going to travel to Earth for 55 million years, and then it's going to reach one of the telescopes slightly before the other one. And this time delay is key for extracting that 2D spatial frequency measurement that's used for image reconstruction. But when you have a telescope in Chile and one in Hawaii and one in Spain, they all are going to have different atmospheres above them. And each atmosphere is going to cause a different propagation delay in the received signal, which leads to an additional random phase in that frequency measurement. So now we've corrupted the phase. And similarly, the atmosphere also causes different attenuation factors in the signal, causing a changing absolute gain term. And so this error is very challenging because ideally we would measure this nice, beautiful Fourier component, the italicized V here, but in reality, we have a completely random phase error that we have to deal with. And then sometimes, and oftentimes we have a pretty bad amplitude error as well. And so this is pretty terrible because at first glance, you know, every measurement we have an amplitude and phase, but we've lost both the amplitude and phase. And so what really do you have left to work with? But in the measurement term, remember that every measurement we make is from pairs of telescopes. And these errors that happen due to the propagation of light through the atmosphere are happening at every individual telescope. So if we had, that means that if we have a third telescope, then the measurements that are formed with that third telescope actually share some of the same corrupting terms, G2 and Phi2. And so we can design imaging algorithms to try to take advantage of the redundant corruption we see across different measurements when solving for our images. So if you're familiar with what phase retrieval problems are, we essentially have to solve a constrained phase retrieval problem. So, however, though, even with these data constraints, we still have the problem of infinite solutions. And so to deal with that, of the images that are consistent with the measured data, there are some that are more likely than others. And so our goal becomes to find an image that doesn't just fit the model data, but is also likely under some sort of mathematical model of what a likely image is. And so we introduce this through image regularization or image priors that we incorporate into kind of a Bayesian, kind of like a Bayesian estimation framework. And so using this idea, we developed a number of techniques to tackle the challenging Event Horizon Telescope data. But note that even if we can develop these methods that allow us to recover single image from this really sparse, noisy data, we still have to be really cautious. And that's because any imaging method we come up with, whether it is a more traditional approach or a fancy new machine learning approach, it's always going to require that we inject some information into the problem about what images look like to recover something back in the end. We have to differentiate between those infinite solutions. And so that is always going to bias our final picture. And for instance, we wouldn't want to accidentally have a preference for more ringy looking images and then be super excited we recovered a ring back in the end. So we had to be very careful when making images. And that meant a big question we faced in dealing with the black hole data was not just how do you make a reconstruction, but also how do we verify what we're reconstructing with our imaging algorithms is real. And we tackled this through a multi-step process. And the first step actually began years before we had even collected data of the black hole. And that was to run synthetic data tests. And we did this through what we call the Event Horizon Telescope Imaging Challenges, where we'd have a team of people simulate realistic data sets that were then distributed so that anyone could try to make an image from them. And the data sets were distributed without any information about the true image used to generate that data. And then different groups would use their different methods to try to make their best guess at what that picture should be. And from this, we then pass these reconstructed images off to a group of a few astrophysics experts that we'd recruit to try to predict what the underlying structure of the true image was from these images. And this was essentially kind of what was going to have to happen when we dealt with our real black hole data, because we didn't know what the true source was going to look like. So we'd have to take our reconstructions and try to come up with scientific conclusions from it. But unlike in the real data case, because the data here is simulated, we could evaluate how accurately the reconstructed images match the true image. So I want to show you a few examples of things we saw in these imaging challenges to show how they informed how we went about actually imaging with M87 data. So here is one example. The true image is on the top. It's also on the top right. It's just slightly blurred. It's blurred to the resolution we expect to be able to kind of recover. And although each image was recovered and on the bottom, it's showing different images submitted to the challenge from different independent teams of people. And although each image was reconstructed independently of one another on the bottom, and they didn't have any knowledge of the truth image, they all have very consistent structure. Each image does look slightly different. You know, some have different wispy structures in different places, and kind of some are flatter than others, but they all kind of point towards the same underlying structure, this kind of ring shape that is brighter on the left side than the right side. But by looking at what is similar and different across these images, we could learn that we could use it to try to gain confidence in certain features, since every imaging algorithm here had a slightly different bias. And so if a feature does appear in some images but not in others, maybe we don't have high confidence in those features. But we also wanted to make sure that we could see something unusual with our methods, right? So we threw in some crazy images to the challenge as well. Here was a submission from another challenge. And the reason I'd like to show this example is because clearly no one was expecting a snowman to be in the center of the galaxy. And obviously our imaging methods aren't either. But we were still able to recover this kind of surprising structure, giving us confidence that we might be able to get we would hopefully, if something was surprising in the center of M87 galaxy, then hopefully our algorithms would be able to see it as well. Although who knows what our final interpretation in that case would be. So based upon these synthetic data tests, we developed how we were going to go and approach the actual black hole M87 data. And we wanted to avoid shared human bias like we had done in those imaging challenges in order to assess common features among independent reconstructions. And so to tackle this, we split about 40 people who worked on imaging, either they developed new methods or they're very knowledgeable at using other methods. And we split them into 4 teams that span the Earth. And these 4 teams were not actually able to talk to each other at all during the initial imaging process. So once we got the data, we split into our teams and we isolated ourselves and worked in our teams trying to make the best image from the data for 7 weeks. And then after 7 weeks, we all gathered together and we revealed the images to one another. And this is what we saw. So these were the images, the first images we ever saw from each of the teams. And this was quite amazing because although each picture was different, similar to in those imaging challenges, they all still reconstructed the same basic structure, this ring of the same size, 40 microarcseconds in size, that's brighter on the bottom than the top. And so seeing these images brought a whole other level of confidence to our results, as we found the same structure kind of no matter the method or person that we used to reconstruct the data. So we kind of, each one had different biases, but it all still kind of pointed towards the same solution. And without having done this test and having different people reconstruct with different methods, I think we would have never achieved the same level of confidence we have in our results. But we still wanted to make sure that we weren't imposing, just because we weren't imposing shared human bias, it doesn't mean we weren't imposing human bias and that we all wanted to still see a ring structure and we're kind of subconsciously pointing it in that direction. So to try to test ourselves on this, we spent the next couple of months essentially trying to break our images. And that led to the third step where we tried to develop methods to automatically reconstruct images without humans making hardly any decisions. And to do this, we coded up 3 different imaging pipelines. As a side note, and I'll discuss this more later, you can download all this code and the M87 data online. So you can download it and run it or modify it as well and see how it affects the images. And these imaging pipelines all have their individual knobs on them, these hyperparameters that are usually tuned by a human user. But instead of having a human tune the hyperparameters, we wanted to instead have the computer search for the best set of settings to recover different types of source structures and then see how that affected the results we got with the M87 data. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center. And then we asked the computer to find the best parameters to recover this disk shape. And then when transferring these exact parameters onto the actual M87 data, although we had searched for parameters beta here that would, trying our hardest to find ones that would give us a disk with no hole in the center, we found that when we fed in our actual M87 data, our algorithm still required us to put the hole there. And by doing this simple training and testing procedure, on many different kinds of, or on different kinds of underlying sources, and finding the sets of parameters that gave reasonable results, searching over, not looking just over one set of parameters, but over sets of parameters, we saw that our methods really always preferred this kind of ring shape. And that was true no matter the day we observed M87 on, or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them to form the image that we showed last year, this ring of light surrounding a black hole, roughly 40 microarcseconds in size and brighter on the bottom than the top. And this image tells us so much about the immediate environment around a black hole, and things that we've learned so much from it already. But perhaps kind of one of the most amazing things is that by comparing this picture to simulations scientists have made for years, we find that the image we've taken is amazingly consistent with a number of these predictions. And also, at the end of the day, really the biggest thing, we can extract the diameter and look at the relative brightness of the ring and learn a lot from it. But kind of at the end of the day, we recovered a ring. And that's something that might now seem obvious, but that was really an ultimate question. Would we see a ring? And I think that's quite exciting. But you might notice, in the simulation I just showed you, it was moving. So is our recovered image of M87 also moving? And it turns out, in fact, it is. So another interesting thing is that we actually observed M87 over the span of a week. 2 days closer to the beginning of the week and 2 days closer to the end. And so we had 4 data sets. We could independently image each data set and then string them all together to form a short movie. And if you play this movie, you'll notice that there's actually some variation, some evolution. So I'll play it for you here right now. It's really hard to see, so I'm going to play it again. There's kind of like it's originally brighter more on the left side, and then it becomes brighter on near the bottom. Play it again. So we don't know exactly what this evolution is caused by, whether it's material rotating or just kind of filaments getting brighter and dimmer. But what we are really sure of is that the black hole is definitely evolving. And that's because it appears in the raw measurements we take with high significance. And actually, getting a hold on a black hole's time variability is quite important for a number of reasons. It not only gives us a window into the dynamics around a black hole, and hopefully an understanding of how their powerful jets form, those galactic scale jets I talked about at the beginning, but it'll also help us in mapping the space-time of a black hole and constraining our prediction of general relativity even further. And so actually the black hole in M87 is not the only black hole we're interested in imaging to get a handle on the question of time variability. In the heart of our own Milky Way galaxy, 26,000 light years away from us, there's a cluster of stars. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the path of this orbiting cluster of stars over decades. And by tracking the motions of these stars over time, astronomers have concluded that the only thing small and dense enough to cause this motion is actually a supermassive black hole in the center of our own Milky Way. And in fact, this discovery led to the Nobel Prize in Physics given just weeks ago for the work of Andrea Ghez and Reinhard Genzel for the discovery of a supermassive compact object at the center of our galaxy, otherwise known as Sagittarius A star. And so as awesome as M87 has been, Sagittarius A star, or Sag A star for short as we call it, might be able to help us better answer these questions. So M87 is a massive black hole. It's huge. It's 6.5 billion solar masses, and Sag A star is teeny tiny compared to M87, only a measly 4 million solar masses. But because it's actually so much closer to us, it appears about the same size in the sky. But since it is so small, that means the gas around Sag A star is orbiting much more quickly. So whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sag A star, gas can make a complete orbit every 4 to 30 minutes. And so we would like to be able to image the time variations around Sag A star. And to do that, we have been developing methods to try to recover not just static images from the data, but full movies. But if you thought recovering a static image was a hard problem, then this is orders of magnitude more challenging, because now we have the same amount of data, but we have to solve for all the pixels in a full movie rather than just a single frame. And so as important as it is to continue pushing on the algorithmic approaches to squeeze more out of the data we've already collected, it's also important to realize that to extract more science, we also have to think about improving not just our algorithms that analyze the data, but also our instrument that collects the data to begin with. And so to help us take better pictures, we're trying to design the next generation array, which expands our network of telescopes from 6 locations on Earth. And we've already been building out the array to get more data, adding telescopes in Greenland, France, Arizona. And the one I'm most excited about is we recently got money to add a telescope at Caltech's Owens Valley Radio Observatory. But imagine, what could happen if we could add 10 more? Well, maybe we could actually make a video of the gas falling into the black hole in the center of our Milky Way galaxy. And being able to do this would be a huge scientific gold mine. But before we just plop down a bunch of telescopes, we have to be really careful. And that's because building a new telescope is expensive, at least millions, but usually tens of millions of dollars. And so we really should try to optimize to find the locations that are going to give us the biggest bang for our buck. And so by developing new machine learning approaches that optimize the future telescope array, we're actually starting to understand where we may be placing our next ground-based telescopes to reveal more of the unseen. And so I don't have time to talk to you about this today, but I'm just really excited about this direction of using computational methods to not just analyze the data, but build the next generation of our telescope. So just wanted to briefly mention that here. And potentially even expand on our telescopes to space. And so hopefully by jointly improving our sensing system and reconstruction methods and optimizing them simultaneously, we may be able to see even more. And so really we're just kind of at the beginning. Now that we have this extreme laboratory of gravity, we're thinking about how we can improve our algorithms, our instruments, improve them jointly to learn more. But before I end, I want to highlight again how it took a huge community of people to make this result possible. Within the Event Horizon Telescope, we had 200 members with different expertises who all worked together to achieve these results. And we're still hard at work. In fact, this week right now, we're holding our collaboration meeting online. But really, this group is just the tip of the iceberg of people who made this project possible. And and as I mentioned before, we have all our code and data sets publicly available online. And you can go online to the Event Horizon Telescope website, eventhorizontelscope.org, to download all the data and imaging scripts. And this serves 2 purposes. First, it emphasizes how important it was that the science be reproducible. You can easily go and make your own images with the data and code we've provided. And second, we wanted to be fully transparent with the methods we were using to recover these images. So hopefully people will look at our methods, not just learn what we've developed, but also build off of them and improve techniques moving forward for both imaging black holes and imaging in other domains too. And after posting all the imaging code publicly, there was a huge amount of interest from the online community. And in particular, our imaging code was made available on GitHub repositories. And just days after the announcement, I was contacted by the GitHub CEO, Nat Friedman, and he was so excited to see we had made our code publicly available. But not just that, he was thrilled to see how many of our methods relied on open source software that had been built up over decades. And by analyzing our dependency tree, they found over 100 different open source Python packages that our imaging code relied on, including SciPy, NumPy, Matplotlib, Pandas, AstroPy, IPython, and Jupyter, among many others. And by looking at all the contributions of people who touched these packages, and GitHub determined that the Event Horizon Telescope images weren't just the work of 200 scientists, but nearly 23,000 people from around the world who over decades contributed to code, methods, and ideas that we relied on to make these images. And so I think this is just one story of how open source software can make a real difference in pushing the bar forward in science and technology. And this extended online community really made it possible for us to pull this impossible feat off. And so together we kind of act as one extended team, and by continuing this tradition of open source and reproducible science, I know we're going to be able to do things that, that at first glance seem impossible. So with that, thank you, and I'm happy to take any questions.
So one question from Ian Mulvaney is, your methods seem to be operating at the outer boundary of detectability given the instruments and what is being observed. What's needed at this point? Sorry, I apologize. I'm having issues here. What is needed to increase the resolution by an order of magnitude or more?
Yeah, so it's a really good question. So we are limited, as I talked about in diffraction. What we can only see at very particular wavelengths that pierce through all the gas and dust, and to see that ring of light around the black hole at near the event horizon. And so we're kind of limited in the wavelengths we can use. And so to get higher resolution, you really need to go to longer baselines. So as I had talked about, for every 2 telescopes, we probe a spatial frequency. And so the longer the baseline, the higher the spatial frequency we probe. And so to get higher resolution, we really do need to think about going to space. And so that's where I just really briefly kind of flipped past it, but that we are talking with people, especially now that I'm at Caltech, talking with people at JPL about the potential of going to space. Of course, it is a big leap to do something like that. The project has been relatively inexpensive as far as science projects go, because we were able to leverage these telescopes that were originally built for other purposes, put specialized hardware in them, and link them together. And so the project was, it's hard to put a cost on it because money comes from many different places, but I think it's roughly less than $100 million, whereas going even one space dish would be, at least from talking to JPL, like $500 million. So it takes it's a much more expensive and would take a long time to get something in space. And so the trade-off of going to space is, do we care more about higher resolution, or do we care about more filling that that measurement space up? And so this is one question that we're actually studying now pretty intensely, especially since we have this NSF grant to build out the next generation of the ray through adding telescopes on the Earth. And where is our balance between that and potentially going to space for higher resolution?
Yeah, hi, thanks for the great work, really awesome. But maybe you can just expand on the topic of how specifically did different imaging teams use domain knowledge in their models? Like where exactly does the astrophysics domain knowledge come into the whole prediction model? That would be really interesting to, yeah.
It's a great question. And actually, it was very important that we limit the amount of astrophysics knowledge, because we're trying to test this idea. So we didn't want to get into the circular argument of putting physics in that we're trying to test, right? So in the stage of imaging, we did not assume anything about gravity or anything like that. It was any physical model was just about telescopes, of how light is propagating through those telescopes. And there's no general relativity or anything kind of assumed there. We didn't assume that the structure was rings at all. In fact, we tried to test against that by doing things like training on images of disks and making sure we would still see the ring even when we tuned parameters for the case of a disk. So the procedure that we took is, first, we did this imaging stage of the blind imaging. After we were very confident in this ring structure, then it got passed on, and there was more model fitting work that was done, assuming physical models of what we expect black holes are. So this was either by fitting crescent models to the data directly, not via imaging, but actually direct model fitting of simple models, or also people spend a lot of time, like I showed this video of the gas kind of swirling around the black hole. So this is called a GRMHD simulation. People spend hundreds of millions of they're very computationally expensive to make these, but these are simulations of how they expect the gas to be flowing around. But they also have parameters, and so we're kind of searching over what set of parameters are most likely to fit the data we have. And so after we were pretty confident of that ring shape, then we could say which of those parameters best fit our observations. But you really have to, every step you have to make sure you say, under the assumptions of this is the set of models, this is the kind of result we had. And at the stage of imaging, we try to remove any kind of physics of gravity from the equation.
Okay, the question was about splitting up into teams, and that process of kind of dividing and then coming together. And I'm curious, was there any pushback on that idea at the beginning? And were there any cons discovered in that process? Or overall, was it kind of just a positive experience?
Yeah, well, getting to that stage took many years, I would say. So remember, there was we worked on developing imaging methods for years before then, and I remember those imaging challenges that we worked on. And I think that it took a while to convince people to participate in things like those challenges, to understand how we benchmark our methods. So I actually came from I come from more of the computer science community. I did my PhD in computer vision, which is where like benchmarking is just very standard there. And I came into the astrophysics community, and they're like, where they're very much farther along than computer science in some ways. As far as benchmarking, I feel like they had a lot to learn. So things like doing these kind of challenges, I think, really helped them. And although it took me a long time to convince them that it was useful, after a while, I think that they realized how important it was that we do this independent imaging. And so, although I think there maybe was some, wanted to get results as fast as possible, I think once people realized how important it was for us to get these right and not screw it up, people were willing to buy into that. And so, yeah, I think it was, it's a balance of doing things fast and doing things right and verifying it. And so, I like to lean on the side, at least for for this. I was very, spent many a night awake making sure that we were, not we were afraid of publishing something that was wrong. And so I think it was important when we spent that time splitting into teams, even if it slowed the process down.
Dr. Bouman, thank you so much for your talk. I wanted to particularly invite you and your team to talk with the PIP user experience folks to let us know if there are any things in the world of installing and dealing with Python packages that possibly could help you out. But also I wanted to ask about bottlenecks and sticking points where, in your opinion, especially, so, your team works, it sounds like, primarily, with Python, and then, of course, you're going to end up working with other languages along the way as well, right? Bottlenecks that you think on a systemic level, if we really got at those, they would be able to supercharge the research of your group and groups like yours.
Yeah, it's a great question. And I'm sure I have many answers. I'm trying to think of on the spot what it is, but I think that especially so one thing is we have to I'm sorry, maybe I can get back to you more with better answer once I've thought about it more, but we ran a lot of these things. They were so computationally expensive that we'd have to run things on clouds, and everyone had so much, and everyone had different environments and things like this. And so this was very a challenge to get around. And so recently we've been using things more like Docker Singularity shells to help us have consistent code and everything. But I think that was a big challenge too, because when you're trying to debug things or understand how sensitive are our methods, you don't want that to be coming into the equation. So I think that it was a slow process from everyone coding up on their own little laptops and running their scripts to us finally using things like Jupyter notebooks better to share things. But I think as we go to bigger and bigger collaboration, we have to make sure to stay organized and use things like this so that we don't waste so much time in trying to understand why are there differences in results that we see across computers.